Beneath the calm blue surface of the Ionian Sea, something vast is on the move. Off the eastern coast of Sicily, the southeastern flank of Mount Etna is slowly, relentlessly sliding toward the deep. This is not a sudden rupture or an explosive eruption. It is a mass of solid volcanic rock, estimated at roughly 25 cubic kilometers, shifting under its own immense weight. A volume so large it rivals entire mountain ranges. A slab of earth heavy enough to fill millions of Olympic swimming pools, and it is moving faster than scientists have ever recorded before. What makes this movement especially unsettling is not what drives it. This is not magma forcing its way upward. This is gravity, acting patiently and without warning. And history shows what happens when this process reaches its breaking point. To understand the risk, we must first understand what lies hidden beneath the water. Just offshore from Sicily, the submerged continuation of Mount Etna stretches downward into the Ionian Sea. Here, the volcano does not end at the shoreline. Its flank continues beneath more than 1,000 meters of water, forming a steep underwater slope composed of fractured volcanic rock layered over weaker clay-rich sediments. Over time, this unstable foundation allows the entire flank to deform, slowly sliding seaward like a colossal landslide paused mid-motion. The geological record shows that this story has played out before. Beneath the Mediterranean seafloor, scientists find chaotic layers of sediment, jumbled blocks, coarse sands, and massive debris fields buried under volcanic ash and marine mud. These are not ordinary deposits. They are the fingerprints of ancient submarine landslides. Evidence suggests that around 8,000 years ago, a large section of Etna's flank collapsed into the sea. When that mass plunged downward, it displaced enormous volumes of water, sending powerful waves across the Mediterranean basin. Those waves left subtle but lasting scars along distant coastlines. While the exact height and reach of that ancient tsunami remain under study, its signature is unmistakable. Disturbed sediments stretch for kilometers, in some cases reaching the African continental shelf. The mountain failed, and the sea responded with sudden violence. Today, scientists see troubling parallels. Modern monitoring reveals that the same portion of Etna's flank is once again in motion. For years, this movement appeared slow and steady, measured in millimeters or centimeters per year. But that pattern no longer holds. Sensors on the seafloor now record episodes of dramatic acceleration. In one documented event, a section of the underwater fault shifted more than 4 centimeters in just 8 days. This was not a single jolt, but a sustained slip unfolding quietly beneath a kilometer of water. Such rates far exceed anything previously observed. They signal a system under increasing stress, where friction and resistance are gradually being overcome. Crucially, the pattern of deformation tells a clear story. Movement is smallest near the summit of the volcano and grows larger toward the submerged edge. The deepest sections move the fastest and farthest. This rules out magma pressure as the primary driver. Instead, gravity dominates the process. The sheer weight of the volcanic flank, combined with the steep slope and weak layers at depth, pulls the entire mass seaward. This kind of gravity-driven instability is not unique to Etna. Similar collapses have occurred at other volcanic islands around the world. But Etna's case is different in one critical way: proximity. Millions of people live along nearby coastlines, directly within the reach of any waves generated by a sudden collapse. While gravity sets the stage, volcanic activity can still influence the outcome. Magma intrusions beneath the eastern flank add internal pressure to the mountain. When magma wedges into fractures, it can weaken the structure and briefly accelerate movement along already unstable faults. These episodes do not cause the slide outright, but they can push the system closer to a tipping point. The interaction between internal volcanic processes and external gravitational forces creates a complex and unpredictable hazard. Understanding this hidden motion requires technology capable of seeing through the sea itself. Traditional tools like satellite radar and onshore GPS stations capture only part of the picture. The real breakthrough comes from the seafloor. At depths of roughly 1,200 meters, networks of acoustic transponders sit anchored across the submerged fault zone. These instruments form a precise underwater web, measuring the distance between fixed points with millimeter accuracy. Every 90 minutes, they exchange signals, tracking even the smallest shifts in position. When the accelerated slip occurred, this network recorded it in remarkable detail. The sensors detected horizontal movement along the fault and subtle vertical subsidence, confirming that the flank was not just cracking, but sliding as a single, connected mass from land to sea. Onshore GPS stations recorded matching displacement along the coast, tying the offshore motion directly to the volcano above. Alongside these measurements, faint micro-earthquakes ripple through the moving rock. Too small to be felt on land, these tremors appear clearly in the data, marking the slow release of stress as the flank creeps forward. Together, these signals leave little doubt. The underwater slope is unstable, and it is actively deforming. To close the gap between detection and disaster, scientists deploy an expanding arsenal of monitoring tools. Pressure sensors on the seafloor measure minute changes in the water column, capable of detecting the first surge caused by moving rock. GPS-equipped buoys float above the fault, relaying real-time position data via satellite. Compact seafloor geodetic stations built for long-term endurance record deformation over years, capturing both steady creep and sudden slips. Fiber optic cables running along the coast add another layer of insight. Using distributed acoustic sensing, these cables act as thousands of vibration detectors, listening for microseismic signals that reveal strain deep within the system. Together, these technologies offer an unprecedented view beneath the waves. Yet a hard truth remains. These systems can detect a collapse as it begins, but they cannot predict precisely when it will happen. The first unmistakable warning is likely to be the movement itself. That reality defines the human risk. Along the eastern coast of Sicily and beyond, more than 3 million people live within the potential impact zone of a tsunami generated by Etna's flank collapse. Cities like Catania sit directly in harm's way, their ports, neighborhoods, and infrastructure pressed between the sea and the rising slopes of the volcano. Nearby towns and villages line the coast, their economies tied to tourism, fishing, and maritime trade. In summer months, the population swells as visitors fill beaches and hotels, drawn by the dramatic presence of Etna on the horizon. Roads, railways, power lines, and pipelines all trace the narrow coastal strip. The economic exposure reaches tens of billions of euros, extending far beyond Sicily to shipping lanes and trade networks across the Mediterranean. For civil protection officials, the challenge is daunting. If a collapse occurs, tsunami waves could reach the Sicilian coast in as little as 15 to 20 minutes. In some scenarios, the warning time could be even shorter. Evacuation routes are limited. Many roads run parallel to the shoreline, with few rapid paths inland. In some towns, a single highway or mountain road serves as the only escape. Planning under such constraints is extraordinarily difficult. Evacuation strategies exist, but many remain untested at full scale. Ensuring that residents, tourists, and seasonal workers understand where to go and how quickly to move is an ongoing challenge. The margin for error is measured in minutes. The risk does not stop at Italy's borders. A large collapse would send waves across the Ionian Sea toward Greece and North Africa. The Mediterranean is a tightly connected basin, crowded with coastal cities and busy shipping routes. A hazard in one corner becomes a shared responsibility. This has driven growing cooperation between scientists and emergency managers across the region. Efforts are underway to link monitoring networks and warning centers, ensuring that alerts travel instantly across national boundaries. The goal is a system where digital warnings, sirens, and public broadcasts activate in unison, regardless of language or jurisdiction. The challenge is both technical and political. Data streams must be compatible. Communication channels must remain functional even during power failures. Public messaging must be clear and universally understood. International drills expose gaps, from delayed siren activation to confusion over evacuation routes. Each exercise reveals how much depends on seamless coordination. The window of 15 to 20 minutes looms over every planning meeting. This limit is set by physics, not policy. No amount of preparation can change how fast waves travel. What can change is how quickly people respond. Beneath the Ionian Sea, Mount Etna's flank continues its slow descent. Centimeter by centimeter, gravity pulls the mountain toward the deep. The geological record shows that this process can remain quiet for centuries, then end in sudden collapse. Whether that moment comes soon or far in the future remains unknown. What is certain is that the risk is real, measurable, and ongoing. It is written in layers of ancient sediment, in the data streaming from seafloor sensors, and in the lives of millions who live along the Mediterranean's shores. Preparedness in this context is not about predicting the exact moment of failure. It is about recognizing the warning signs, closing every gap in response, and acting before the unthinkable becomes reality.